So what we already have is some basis for Rn and some other vectors in Rm, and this equation. Anything that is in Rn will go to the column space, and we know now that V is orthonormal because we completed the basis, and it's an n by n matrix, and it's orthonormal. It contains the basis vectors for the row space and the basis vectors for the null space, which is a complete basis. So that means we can multiply both sides by V inverse, which is the same as V transpose because it's orthonormal. So we have an expression for A like that. So that means if you just take the transpose of that, what I'll get is A transpose. This is the product of transposes in the reverse order. So V transpose transpose and U transpose. Now if we can actually satisfy our requirement that we want U to be an orthonormal matrix, then we can say that U transpose is actually U inverse. So if that is true, if this is true, then we can take this equation, the red equation, and multiply the blue equation by it. So multiply on the left. So A transpose A V is going to be equal to this expression here, V sigma U inverse times U sigma. So what do we have in here? If this matrix is actually orthonormal, then that is just I. And then you get sigma transpose sigma, which is just sigma square because it's a diagonal matrix. So what do we get? We get A transpose A V is equal to V sigma square. So that is what we will get if we ensure that U transpose is equal to U inverse. If that is our requirement, and if you can satisfy it, then we will get this equation. If you look at that equation, what's that telling you? In order to see that equation better, let's call A transpose A by a new letter B. So if you have the eigenvalue decomposition of B, then you have B times some matrix, the eigenvector matrix, is equal to the eigenvector matrix times the eigenvalues of B. So compare this guy with this. What it is saying is that V is actually the matrix of eigenvectors of A transpose A, and sigma square is actually the matrix of eigenvalues of A transpose A. So that's what it is telling you. So Vi, each vector in the matrix V, is an eigenvector of A transpose A. Remember, A transpose A is our gram matrix. It's coming up again here with an eigenvalue that is equal to sigma square, sigma I square. So that way we can actually compute all the V's and all the sigmas. So it's already there. So we found our special basis in the input side such that it will go to an orthonormal basis on the output side that we implemented by insisting that this be true, this be equal to identity matrix. And similarly, if you actually want to compute UI, what you will do is to take AA transpose and basically do the multiplication the other way, and you will get the eigenvalues equal to sigma I transpose again, sigma I square again, and you will get UI to be the eigenvectors of A transpose. So what is important to know is that A transpose A and AA transpose have the same eigenvalues. The non-zero eigenvalues are the same. So one of them will have some number of zeros, the other one may not, but the non-zero eigenvalues are the same. This can be proven fairly easily. Now we are going to say that we found sigma I square as the eigenvalues of A transpose A, the gram matrix, and we're going to take the positive square root as the values in sigma. Sigma is a positive square root of the eigenvalues of A transpose A or A transpose because they are the same. So what we have is a matrix that is m by n. Is a general matrix. It doesn't have full rank. So rank is actually less than m or n. And we constructed the basis for the input space, and the basis for the output space will be just the basis of the column space union with the basis of the left null space. Started from the basis for the input space, and then we did the SVD and we got a full basis for the output space Rm. That would turn out to be some vectors. The first R vectors actually would be the basis for the column space. The next m minus R vectors will be the basis for the left null space. So that's what we will have. So our matrix A can be written as a matrix U, which is a basis for the output space codomain Rm. So it is an m by m matrix, and that has a U hat that is just the basis for the column space, and then there are m minus R columns that are the basis for the left null space, times we have have some scaling factors, and again we have R of them, which will be in the diagonal positions of this sigma matrix, and then everything else will be 0. And then we have the V transpose, and V is actually a basis for the input space Rn. So V transpose is also n by n, and in V transpose the first R rows are going to be the basis for the row space, and the next n minus R rows are going to be the basis for the null space. Now if you look at it once more, you can see that the scaling factors are non-zero only in this region. So when you multiply this by this, the bottom n minus R guys are going to be multiplied by zeros, so that will not really give you anything. Similarly, the left m minus R guys here are going to be multiplied by the zeros here, so that also will not give you anything. So we can actually write the economic version of SVD by just considering the hatted part, U hat, sigma hat, and V hat transpose. So that's what I wrote here. Whatever I have here, those zeros will kill the basis for the null space and the left null space, so that part is not that critical. Vectors in the columns of V are called the right singular vectors, and these are the left singular vectors. So we can ignore the null space here and the null space here. That is the full SVD or the smaller economic version of SVD. Both are accurate. Okay.